Hello friends, today I will solve a LeetCode hard problem that was asked in weekly contest 402. So the problem is peaks in array. So what the problem says, a peak in an array ARR is an element that is greater than its previous and next element in ARR. So an element is a peak element if it's greater than its previous and next element. So we are given an integer array nums and a 2D integer array queries. So we have to process queries of two types. So in the first query, we are given two indexes li and ri. We need to determine the count of peak elements in the subarray from index li to ri. Similarly, in the second query, we are given an index I and a value. So we need to update the value at index I. So we need to return an array called answer containing the results of the queries of the first type. And it's given that the first and last element of an array or a subarray cannot be a peak element. So let's understand this problem with the given examples. So in the first example, we are given a nums array and we are given two queries. So in the first query, we'll update the value at index 3 to 4. So these two will be updated to 4. So after first query, the nums array becomes 3, 1, 4, 4, 5. And the second query says we need to find the peak element in the subarray from index 0 to 4. So index 0 to 4 is the total length of the array. So here we can see no element is greater than its previous and current element. So the number of peaks in the current array will be 0. So I have taken the first example. So the brute force approach will be for update query, directly change the value at that index. So the update will be order of 1 or big O of 1. And for search query, we will linearly search the array and count the number of peak elements. So this will be big O of n. So at the worst case, let's say all the queries when all the queries are search query. So the time complexity will be big O of m into n. That is m is the size of queries array. So this approach is not optimal. So it will give TLE for the given constraints. So let's look at another approach. So we are given queries of two types, search query and update query. So we know that the data structure that is used to process queries of these two types is segment tree. So now I'll discuss an approach that is based on segment tree. So a segment from L to R will contain count of peak elements in the subarray from index L to index R. So the idea is we'll divide the problem into two intervals, that is L to M and M plus 1 to R. So let's say the result for this subarray is R1 and the result for this subarray is R2. That is the count of peak elements in these two intervals. So to compute the result for L to R, we can do R1 plus R2 plus we need to add something because in the first subarray value at index M can't be a peak element because we know that in an interval the left and rightmost element cannot be a peak element. Similarly, the value at index M plus 1 can't be a peak element, and we need to check if value at index M and index M plus 1 is a peak element. So if the value at index M or at index m plus 1 is a peak element, then we will add that count to the count r1 plus r2. So first I will construct a segment tree for this example. So the root element will contain from index 0, 1, 2, 3, 4. So root element will contain from index 0 to 4. So the mid will be 2, that is the left will be from 0 to 2, and the right will be from 3 to 4. Similarly, then I will again subdivide the interval 0 to 2 to 0 to 1 and 2 to 2. Then again I can subdivide this interval from index 0 to 0 and index 1 to 1. So I cannot divide this subinterval now because this is a subarray of size 1. Similarly, this is a subarray of size 1. This is a subarray of size 1. Now I can divide this interval. So here it will be 3 comma 3, and now another interval of size 1, that is 4 to 4. So we know that subarray of size 1 and size 2 will have peak count 0, because for a subarray of size 2 also the left and right index cannot be a peak element. So for subarray of size 0 the peak count will be 0. Similarly, for subarray of size 2 peak count will be 0. So for 0 to 2 we can see the value is 3, 1, 4. Now this is 0, 1, 2. This is L, this is R, this is mid. The result for the left subarray is 0 and the result for the right subarray is 0. Now I'll check for the middle element if it is a peak element. So I can see the middle element value is less than the elements on its right or left. So the middle element is not a peak element. So I'll add the result of left and right subarrays. So for subarray 0 to 2, there are no peak elements, so output will be 0. Similarly, I will consider for index 0 to 4. For left subarray, the peak count is 0. Similarly, for right subarray, the peak count is 0. Now I'll check for the middle and middle plus 1 element. So the middle element is a peak element because it's greater than the element on its left and the element on its right. So the peak count for the subarray 0 to 4 will be 0 plus 0 plus 1, that is for the middle element. So in the update query, it's given that update the value at index 3 to 4. So here I'll update the value at index 3 to 4. So I'll start from the root. I can see index 3 is within the range 0 to 4. Then I'll check its left. Index 3 doesn't lie in the range 0 to 2. So I will skip this left subarray. Then I'll check for the right subarray. I can see index 3 is part of this subarray. So I'll go its left. Now we have reached a subarray of size 1. So I'll keep the result same. Then I'll go to the right subarray, that is 4 to 4. Index 3 is not part of this subarray. So I'll return. Then I'll update the subarray from 3 to 4. I can see this is a subarray of size 2. So the value will be 4. Now I need to update for the root. So in the left the value is 0, in the right the value is 0. Now here at index 3 the value is updated to 4. Now I need to check for the middle element and the middle element plus 1. So I can see the middle element is not a peak anymore because on its right there is a value 4 which is same as the current value. So this index is not a peak element anymore. Similarly, the value at index m plus 1 is not a peak element because the value on its left is equal. So at the root I'll update the peak count to 0. Now in the search query I need to search for index 0 to 4. The root is the subarray from index 0 to 4, so I'll directly return 0. So the output will be 0. So now I'll consider the second example. So here we are given a nums array of size 6 and 3 queries. So first query is a update query and these two queries are search query. So I'll construct a segment tree. So the root will be from index 0 to 5. The left will be from index 0 to 2 and the right will be from index 3 to 5. Similarly, as the subarray is of size greater than 1, I'll compute the middle and I'll go to the subarray 0 to 1. Then I'll go to the subarray of 2 to. Now this is a subarray of size 1, so I'll stop here. Similarly, the left is a subarray of size 2, so I'll again break it. Now this is a subarray of size 1 and 1 comma 1. So this is also a subarray of size 1. Here I'll again from 3 to 4 and on the right it will be from 5 to 5. Again I will break it. So this is from 3 to 3 and it's from 4 to 4. So first I need to construct the segment tree. We know that peak count for subarrays of length 1 and 2 is 0. So 3 to 4 is a subarray of size 2. Similarly 0 to 1 is a subarray of size 2. So now I'll compute the peak count for subarray from 0 to 2. So this is a subarray. This is the L, this is the M, this is the R. So we can see for middle element it's not a peak element. So I'll add the left and right count plus 0 because middle element is not a peak element. So the peak count for this subarray is 0. Similarly for 3 to 5 I can see the middle element is not a peak element. So peak count for this subarray will be 0, that is the left count plus right count plus 0, that is 0. For the subarray 0 to 5 we can see the middle element is a peak element. The peak count for this subarray will be left count plus right count plus 1, that is 1. So now I'll first take the update query, that is to update the value at index 2 to 4. So if you run the update query, because the value remains same, so at the end the segment tree remains same. Now I'll check for the search query. So I'll take the first search query, that is 102. So we need to search in the range 0 to 2. So you can see the range 0 to 2 lies within the range 0 to 5. Now I'll go to its left. So this subarray is from 0 to 2, which is same as the subarray given in the query. So I'll directly return the result for this, that is 0. Similarly, on the right the subarray is from 3 to 5 and the subarray we are looking for is 0 to 2. So both the subarrays don't intersect. So I'll directly return 0 from here. So from the left we returned from the subarray result 0 to 2. So the output will be 0 because we can see the subarray from index 0 to 2 the peak count is 0. Now I'll consider the next subarray, that is from 0 to 4. So I'll start from the root. The subarray 0 to 4 intersects with the subarray 0 to 5. So now I'll check for its left. So in the left we can see the subarray 0 to 2 is subset of the subarray 0 to 4. So I'll directly return 0 from here. Then I'll check for the right. The subarray 3 5 intersects the subarray 0 to 4, but it's not a subset of the subarray 0 to 4. I'll check for its left. I can see this subarray 3 to 4 is a subset of the subarray 0 to 4. So I'll directly return 0 from here. And I'll check for the right. On the right the subarray is 5 to 5, which don't intersect with the subarray 0 to 4. So I'll return. So from this subarray 3 to 5 I'll return 0. So on the root I'll check for the subarray that is 0 to 4. So the subarray from 0 to 4 is 4, 1, 4, 2. So for the root, the middle element is at index 2. So I can see the middle element lies within the subarray 0 to 4. So I'll check if the middle element is a peak element. So we can see the middle element is a peak element. So I'll add the result from left and right, that is 0 from the left and 0 from right plus 1 as middle element is a peak element. So at the end, the output will be 1. So for the second search query, the output will be 1. So we know that for search query, the complexity is big O of log n, and for update query, the time complexity is big O of log n. So the time complexity will be big O of m into log n, where m is the number of queries. So now I'll code the solution. So first I'll declare a segment tree. Then I'll write a method called construct segment tree, which takes the parameters nums array, int segment start, int segment end, and int segment index. So if the segment start is same as segment end, I'll store the result as 0 and I'll return, because we know that the number of peak elements in a subarray of size 1 is 0. Then I'll compute the middle. Then I'll construct the left subarray, that is the subarray from index segment start to mid, and the segment index will be 2 times current segment plus 1, and the construct subarray returns the number of peak elements for the subarray from segment start to segment end. So here I am adding the left segment peak count, and here I am adding the right segment peak count to the current subarray count. So if the subarray size is greater than 2, because we know that subarray of size 2 can't have a peak element. So if the size is greater than 2, then I'll check if nums of mid is greater than the nums of mid plus 1, and I'll check if nums of mid is greater than the nums of mid minus 1. That is, I am checking if the middle element is a peak element or not. So if it is a peak element, then I'll increment the current count. So if the element at index m is not a peak element, now I'll check if the element at index m plus 1 is a peak element or not. So if the element at index m plus 1 is greater than the element at index m, now I'll check for the element on its right, that is if m plus 1 is less than the ending index, and if nums of m plus 1 is greater than nums of m plus 2, then it's a peak element. So I'll increment the current peak count. At the end, I'll return the peak count. So now I'll write a method called update segment tree, which takes nums array, segment start, segment end, and the segment index. Then it will take. So here the construct segment tree, the right call is from mid plus 1 to segment end. So the update segment tree takes the parameters segment start, segment end, segment index, then the index of the nums array to update, then the value to update. So first I'll check if the current index doesn't lie within the segment subarray from segment start to segment end. I'll directly return if index is less than segment start or index is greater than segment end. I'll directly return else if segment start is same as segment end. So I'll update the value in nums array. Then as it's a subarray of size 1, the pick count will be 0. Then I'll return 0. This process is same. I'll compute the mid. I'll declare result variable to store the current result count or to store the peak count for the current segment. So if the subarray size is greater than 2, then I'll check if the element at index m is a peak element. I'll update or increment the result. And if the element at index m plus 1 is a peak element, I'll increment the result. At the end, I'll assign or I'll store the result at segment tree. Then I'll return the result. Now I'll write another method called search segment tree. It takes the parameters nums array, int segment start, int segment end, int segment index, int query start, and int query end. So I'll first check if the query interval intersects with the current interval, that is, so if the segment start is greater than the query end, or if the segment end is less than the query start, then it means the segment and the query interval don't intersect. So I'll return 0. And next I'll check if the current subarray is a subset of the query subarray, that is, if segment start is greater than equal to query start and segment end is less than equal to query end, I'll return the result, that is value of segment tree at index si. Now I'll compute the mid element. I'll declare result variable. I will call for left and right, that is I'll call for search segment tree and the parameters will be query start, query end. Similarly here the parameters will be query start, query end. So I'll call for left and right subarray. So now I need to check if the middle element is a peak element. So the middle element should be greater than the element on its left and it should lie within the query interval. So the middle index should be greater than query start and middle element should be less than query end. Then I will increment the result. Similarly for the element at index m plus 1. So it should be greater from both the elements on its right and the index m plus 1 should lie within the query. So m plus 1 should be greater than query start and m plus 1 should less than query end. So if the index m plus 1 is greater than query start and less than query end, then I'll increment the result. So at the end I'll return the result. So now I store the length of nums array in a variable n. Then I'll construct the segment tree. I have declared the segment tree here. Now I'll assign it. So we know that the length of the segment tree can at max be 4n. So I'll assign an array of size 4n. Then I'll call the method construct segment tree. I'll pass the nums array, segment start as 0, segment end as n minus 1 and segment index as 0. Then I'll declare a list of integer result to store the result for search queries. Then for each query I'll check if it's a search query, then I'll call search segment tree method and I'll pass nums array, segment start as 0, segment end as n minus 1, segment index as 0. Then query start as q of 1 and query end as q of 2, and whatever the value returned by the method search segment tree, I will add it to the result list. Else, if it's an update query, then I will call the method update segment tree. I'll pass the values nums, segment start as 0, segment end as n minus 1, segment index as 0. Then the index of the element to update is q1 and the value to update, that is at q of 2. So at the end, I'll return the result array. So let's run it for the sample test cases. The sample test cases are running fine. Now I will submit it. So you can see it's working as expected. So what we are doing here, first we are constructing the segment tree. Then for each query, we are either searching or updating the segment tree. So each operation is big O of log n operation. So you can say the time complexity will be big O of m into log n, where m is the total number of queries. That is the length of the queries array. So I'll upload the code in GitHub and I'll attach the link in the description. Please do check it out. So the time complexity is big O of m log n, where m is the number of queries, and the space complexity is big O of n, because I'm declaring an auxiliary array of size 4n for the segment tree. So I can say the space complexity is big O of n. Thank you.